thank you for organizing this session and inviting me. So I'm going to take a little bit more of a higher level approach to this topic and talk a little bit more about reproducibility and replicability, because I believe we are on a very unique time where there are the right tools and the right publishing mechanisms for all of us to be doing what we love, doing science in a much better way. So before I jump into the actually nitty-gritty practical advice, let's define a few terms. So those are definitions we're going to use for the next 15 minutes, and there are lots of discussions about what these things actually mean. And I would recommend you to check out this paper over there discussing all of these definitions. But for now, let's just agree that reproducibility is basically saying whether you can recreate the same result using the original data encode, you or someone else. And replicability, or making a replication, is actually recreating the same result using a newly acquired data set with the same or practically similar experimental design. Okay, so with this definition, let's have a look at reproducibility. So first of all, is this useful, and what is it useful for? Well, first of all, reproducibility is extremely useful when you are in a situation when you submitted your paper and you jumped into a new analysis and your computer basically got lost or burned down in your house. And your reviews come back, and what you do, you have to jump back into that situation, that environment where you have to make all of those changes. So it's basically traveling back in time. And ladies and gentlemen, if you get reference from this picture, it means that you're officially old. But it also is a way for other people to take outputs of your research and build on top of it, and also verify the outputs of it. So the question is, how can we achieve those feats? There are three major components of reproducibility. There's data, code, and the environment in which the analysis has been performed. In terms of data, it's basically a necessary but not sufficient element of reproducibility. So you need to have access to data to be able to reproduce a particular result. So I encourage everyone to publish their data. And there are two major databases that allow submissions, unsolicited submissions of data. One of them is OpenNeuro, and the other one is FCPND. There are certain ethical restrictions that I don't have the time to go into, and there are also options provided by different institutions and universities to provide institutional protected archival of research data, and that also fulfills this purpose. And then there is code. So it's not just about publishing code or making the code accessible. It's also about automating your analysis. So avoiding manual step as much as possible, which is not only a good practice in terms of reproducibility, but also it's good practice in terms of saving time. So if you have to do something twice, write a piece of code for it. You can also take advantage of well-maintained reproducible pipelines that use software containers, which we're going to talk about in a moment, and there are strongly versioned, such as the automatic analysis, CPAC, or fMRI prep. The other aspect of reproducibility is the environment, which I've mentioned in the beginning. And you might be asking, like, what is this environment? Is this the temperature of the room I was doing the analysis in? Hopefully that will not have any influence on your analysis. But other details that you might think are not important actually are. So in this paper by Tristan Glattard, they compared the influence of different versions of the same operating system, so that was CentOS, and the same version of FreeSurfer on the cortical thickness. And they found significant differences basically caused by different libraries that are not shipped with FreeSurfer itself on on the results. And this is pretty scary, but also means that if someone tries to reproduce your analysis using a different version of the operating system or a different version of FreeServer or other toolbox you use, they might fail to do it. So therefore, we need to be more diligent in the way we describe, or even better, distribute the environment we do the analysis in. Luckily, there are technologies right now that enable us to do this. And those are software containers. This is basically a technology that captures all of the libraries, programs, and other pieces of configuration and code on top of the Linux kernel. And all of these pieces are captured in one neat package that can be later reused in a new environment. So this allows you to do your analysis, install the specific versions of software that you need for that particular analysis, and then freeze that, ship it to a repository, switch to a different project, use different software, update the software you use. When your reviews come back, you can go back in time to the particular environment you were in. And then you can distribute this environment together with your code. And there are two major implementations of this technology which are interoperable. One of them is called Docker. It works very well on Windows, Linux, and Mac, as well as in the cloud. And the other one is called Singularity, which is specifically designed to work on high-performance computers or multi-user cluster that many of us have the luck to have access to. And I actually have an educational session tomorrow in the Open Science Room at 10:30 a.m. About those technologies. So if you want to practically learn how to use them, please come. And then we also have the code itself, the analysis. Preprocessing is not everything. Every higher level or second level analysis would have its own unique configuration and code, and that also needs to be shared. So I recommend you learning and using Git and GitHub for versioning and sharing this code. There are plenty of different resources, and I'm also going to point out to some of them how to learn these technologies. They all not only provide you the way of sharing the code and managing the code, but also maintain collaborations with your colleagues on the same code base. And they allow you to freeze the code base using tags and releases. And finally, I also recommend using this addition on top of GitHub called Zenodo, which will archive your code and give the DOI that is not only citable, but also have some guarantees in terms of long-term sustainability from the CERN Institute. Well, I've mentioned that there are some training opportunities. Many of these tools and technologies are being taught on various educational events that are popular in our community. One of them is called BrainHack Global. Maybe a raise of hands who participated in a BrainHack Global event. Okay, that's great. That's great. You filled the whole room. Okay, that was a bit aspirational. So BrainHack Global is a distributed event where there are hackathons or meetings for developers and people teaching all of these tools in different locations all around the world at the same time. There are lectures that are being streamed between those locations, so that allows you to engage with your local community as well as make connections with a global community. So you can learn without actually flying to any location. But if you do want to fly to a new location, I recommend applying to NeuroHackademy, previously known as NeuroHack Week. But because it was extended to 2 weeks, they had to change the name. So NeuroHackademy, it's a mouthful, is a fantastic event organized in Seattle once a year. It's a summer school, which is a combination of tutorials and collaborative work on short projects. And definitely recommend checking it out and applying. And finally, there is our very own OHBM hackathon. So before this conference, we had a hackathon here at the local university for 3 days. It was a fantastic event. Many of the tools I was talking about have been taught there. So next year, I recommend you to apply and join the hackathon as well. Okay, we talked about replicability, and now, we talked about reproducibility, and now let's talk about replications, or replicability in other words. So first of all, if I do have to reiterate that, replication is really the best way for the community to verify credibility of a finding. If a finding does replicate multiple times, it means that it is a strong evidence of its survival and translation to the clinic. So the question is really what makes a good replication and how we can have more replications in our community. So to help with that, we started the OHBM Replication Award, basically to promote replication by highlighting the best replication studies as well as their authors. So last year, the first edition, Walter Bockel, won the award, and this year you probably have been to opening ceremonies. Benedict Sunderman received this honor. Both of them got it for excellent papers. Bockel et al. Published a study of many different brain behavior relationships where they looked at various different effects, and I think they've tested 19 of them, and only one of them replicated. Benedict Sunderman and his colleagues looked at unipolar depression based on resting-state connectivity. That was a multivariate pattern analysis study with a very high-powered large sample, and they also struggled to replicate the accuracy that was previously reported. And that study was very important because of its clinical application. So you might be wondering, who's going to get the award next year? Well, that person might be sitting in this room. I encourage you strongly to apply for this award. It's a great opportunity to highlight your work. But let's get back to the question of what makes a good replication. In the Replication Award, we've been evaluating replication on 2 dimensions. One of them is basically how important the particular study is. So whether it has an ability to change clinical practice or influence policy, or whether it actually opened up a new subfield of research and therefore is a foundation for many other researchers. But also whether it is a debated study, whether people are actually questioning or confirming its findings. And then the other dimension we look at is the quality of the representation itself. Is it pre-registered? Was the protocol that was used in the replication actually consulted with the original researchers? Is the team replicating the study independent from the original team and therefore unbiased? Is the sample size sufficient? And whether they're using current academic standards, for example, outlined in Kobida's report. And also whether the departures from original protocol, because, well, you cannot enter a river twice, whether those departures should not change the conclusion of the original study. So when you think about those 2 dimensions, you can think of studies that are on a very important topic but not executed or very well, or studies that are very well done but address a very niche topic. And then in the upper right corner, those are the Replication Award winners. So, as we heard from our previous speaker, many of the neuroimaging studies are underpowered, which means that a properly powered replication is likely to yield a null result. And then we also know that publishing null results is very tricky. So that means that if you do a replication, you might be facing some challenges in publishing the results. But luckily, there are new publishing mechanisms right now that enable us to publish replications and null results without this uncertainty. The mechanism is called registered reports, and basically it boils down to peer review of your design before the results are known. So you write up the motivation design of the study and your hypothesis, and you send that to the journal, and the journal evaluates it, sends back its comments. It's a normal peer review done by your colleagues. And then if that design is good enough, you get preliminary acceptance. You go collect your data, write up the results, and independently of the outcome of the analysis, you are guaranteed to publish the paper. And there are over 100 different journals, including Cortex, Neuroimage, and Nature Human Behavior, that take part in this program. So I strongly recommend you to publish your replications here, because you know the protocol already because you're replicating someone else's study. Okay, to sum up, I was talking about reproducibility, which can be achieved with data sharing, code version control, and software containers. And then I also argued that replication studies not only require careful planning, but can also be published efficiently using registered reports. And that's all from me. I've used work from many, many people in this talk, but I want to actually end on a different slide and encourage you to check out this website. Thank you.